Okay, let's extend how we convert vectors from 2 dimensions into 3 dimensions. So this r to the little 3 here represents r cubed. In other words, we have a real number line along the x-axis, then another one in the y-axis, and then a third one in the z-axis. So we could call it r times r times r, or r cubed. So what we're going to do is, first of all, in terms of I hat, j hat, that were along the x and y axis, now we have a k hat that's going to be along the z axis. The components we're going to be using, instead of just a, b, as stretch factors of each of the standard basis vectors, we're going to have a, b, and c. So c will stretch out the k hat standard basis vector. And then direction angles will be using alpha, beta, gamma. So the first 3 letters of Greek alphabet. Geometric version of the vector is as before. We have the magnitude and then the direction quoted. In terms of the direction that we would quote with alpha, beta, gamma, you do not need all 3 of them. 2 of them will be sufficient. Just like in 2 dimensions, if we have this angle theta, which is close to the x-axis, there is another angle from the vector to the positive y-axis. We didn't need to quote that because it's the theta actually determines the other vector or the other angle as well. So moving on, we'll do an example of that later on. So if you didn't get that, it will be clear as we solve an example. So for conversion for algebraic to geometric, like before, we have the extension to 3 dimensions of Pythagorean theorem. In terms of the angles, this theta could have been quoted instead of toa, but using ka of SOHCAHTOA. So we could have said it is adjacent over the hypotenuse, and hypotenuse ends up being magnitude of the vector itself. So that could have been our formula. Now we're going to use cosine always for 3 dimensions. You'll see the reason behind that as well when we do an example. So alpha would be cosine inverse of A, so the first component over its magnitude. Beta would be the second component, B over the magnitude, and so on. And to convert backward, it's going to be vector is the magnitude of the vector plus or times the u hat, which just represents the direction. So this is the unit vector, and it's going to be just cos alpha, cos beta, cos gamma. So you'll see how that's used in an example. So how do we convert 3-dimensional vectors? So before we do that, let's discuss how to sketch a 3-dimensional vector. So I'd like you to always think of the x-axis as pointing out directly at you. Y-axis will be horizontal, going to the right, and positive z-axis will be going up. So this vector u could be rewritten from scalar form into this linear combination form. So 3I hat, let's draw this without using the grid. So it's very hard to tell what's happening here. But this is supposed to be showing you that it's going 3 units straight at you, then 1 unit to the right, and then 4 units down. And the overall vector would be where it began to where it ended up. So let's repeat that on the grid itself. So take the first component and draw a length of size 3 along the positive x-axis. Then the next one is positive y-axis component. So draw it along the y-axis first, but then move it over to where you left off from the red. Then -4, draw it again on the z-axis first, negative, so it's on the bottom, but then transfer this over to where you left off from green. This kind of is the beginnings of a box. I'd like you to finish that box, like so. After the box is drawn, you're going to draw the vector from the origin pointing at the left, the ending where you would go first outwards to the right and then down. So that is where the arrow would be of the resultant vector. So now let's move on to how to convert this. So to find the geometric vector, you need to know its magnitude and directions. So magnitude is just found by Pythagorean theorem, the extended version. And some people have asked me, so how does this work? So I'm going to just do a brief explanation how this Pythagorean theorem got extended. So here's a picture of this box. We're going to first of all find, using Pythagorean theorem on this triangle over here, the top portion of this box, because it's a 90-degree angle over here. So x would be using the usual Pythagorean theorem. Then I'd like you to think of this plane right here, slanted from this corner to that corner, and we're interested to find out this purple vector size. Well, that also creates a right triangle with 90 degrees over here. And so x squared plus 4 squared would be equal to this diagonal squared. And so x squared plus 4 squared, we know that this x, if you square this, the root will disappear and it will be placed over here, which is exactly what this is saying. And so when you evaluate that, it would be square root of 26. And then to find the direction, alpha, beta, gamma, you want to do cosine inverse of the first component divided by the magnitude, and so on. Now, here's the reason why cosine is used, not sine or tan. Sine inverse will never give you an obtuse angle. Same thing with tan inverse. And so it's the smartest decision to use cosines for the directions. And so the geometric version of this vector would be, this is the magnitude, and then you could quote all 3 direction cosine angles, or you could just quote 2 out of the 3. Let's convert backward. So if you were given direction cosine and the magnitude, how do we create algebraic version? So you would say it's a magnitude multiplied by this unit vector, which is from the direction cosines. We do not know this gamma here, but we do know that this unit vector has size 1. So magnitude of this vector is size 1. Magnitude is square root of all the components squared, added together. Square both sides, you'd get this. And you could plug in the angles provided for alpha and beta. Work this out. And when you do a square root on the second last line, you'd get positive and negative. And so you could leave it off here, or you can actually find gamma to be 60 and 120 for the 2 versions. But technically, you could have just left it here because this cosine gamma, we know what it is equal to, positive or negative half. So that's all you needed to do to quote your vector in algebraic form. This is positive, negative, a half, or you could use the decimal versions for this vector. And lastly, this is an example. I'm not going to do all of it. I'm just going to find one specific vertex to show you how you could use algebraic vectors to help you find points. So here we are given a parallelepiped. So it's basically a 3-dimensional version of a parallelogram. You're only given A, B, C, and E points, and you're supposed to find all the other vertices. I'm just going to do point F. So as we've discussed before, point F, the notation for the point F is identical to how vector OF looks like. So a vector that has the origin at, the tail at the origin. So I don't know where the origin is. So let's say it's over here. So OF, if I know this vector in algebraic way, then I will know the point F itself. So choose a root of your liking. It doesn't really matter. So I said I'm going to go from O to A, then A to B, then B to this F. I read this out in vector notation. Then I'm going to split up A and B to say I'm going to go from A to O first and then OB. The reason why I want to do that is because all of these points that I want to use, I cannot be adding or subtracting points. But if I were to convert each point to think of them as if they're vectors from the origin pointing at the point, then those vectors I can actually do operations with. So every single one of these, I want something to do with origin within all of them. So AB, I've done it. BF, I first of all think about it from the picture, from B to F is the same thing as A to E, right? So you could replace it like that if you wish. So you don't want to do it with origin right away, because notice how up here we don't actually have point F. So that's what we're looking to find. So you want to rewrite BF so that you're not using point F. So it's AE. There is another vector CG that is parallel too, but notice how we don't have G either. So you want to use what's provided for you. Then vector AE, you could split it up as well using the origin. So here's the result with everything. And remember, this first one, OA, is ready to be used with this coordinates of the points, but A to O is incorrect still. So we want the tail to be at the origin. So you would rewrite this one by swapping the order and that one over here. These end up canceling. And so every single vector here now is from the origin pointing at the point. And so we can actually use the same notation as points for these position vectors now and do the operations with them. And at the very end, don't just leave it like that. Actually quote and say, rename this. This is point F now, not vector. And then you could use the same notation on that side.